Hello everybody, in this lecture we will be solving 1995 IMO problem number 6. We are given 2p elements, 1, 2 up to 2p, where p is an odd prime, and we would like to select p element subsets from this set such that the sum of the p elements in those subsets would be divisible by p. So first of all, notice that it is possible to choose the total number of p element subsets is 2p, choose p. Alternatively, I can partition this set 1, 2 up to 2p as follows: 1, 2 up to p union p plus 1, p plus 2, up to 2p. And let's simply call this as x and this as y. So this is just x union y, our original set here. We can call the original set probably as S. Now what I have in mind is the following. An alternative way to count this is, and so total number of p element subsets would be, well, we have the set x and y, so that's already 2 plus, and what we can do is we can pick k elements from this set and then p minus k elements from this set for k equals from 1 to p minus 1. So therefore, as a result, so that would be the sum for k equals 1 to p minus 1. So choose k elements from set x times choose p minus k elements from set y, and that's exactly the count. So we were able to count it in two different ways. Now what we need is, among these 2p choose p sets, how many of them has the sum of its elements divisible by p, or congruent to 0 mod p, a remainder of 0 in mod p. We will do the following trick. So take any k element subset of x, and let's call this as z, I guess. Consider z sub 0. Let's call it z sub 0. So this subset is z sub 1 all the way up to z sub k. So this is a k element subset of our set x. So now I will do the following. I will create a cycle by doing the following thing. I will add 1 to all the elements in this set, so zk plus 1, and I will calculate it in mod p, and I will continue doing the same trick. So I will come up with 2 plus 2, I should say, in mod p again, and I will continue this procedure all the way to z p minus 1, because I'm calculating in mod p, right? So z1 plus p minus 1 dot 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 zk plus p minus 1, again in mod p. And now I claim the following. Look at this. So we have p subsets that we have created, and I claim that if I calculate S of z0, S of z1, and so on, I claim that if you check this list of p numbers where so what I mean by S of, I mean maybe I should use a different notation because I don't want it to get confused with the other S. I will say it lowercase. Let's use lowercase m, for instance. So the so the lowercase m of a set z of any set is simply the sum of the elements of that set. So I claim that the sum of the elements of these sets form a complete residue class, in mod p. Okay, so one way to recognize this is to observe that mz p is not equal to m of zq for any set here in this list. So all these sets, when you sum their elements, will give you a different remainder in mod p. But then notice that we have p sets here. Obviously there are p choose k ways to pick k elements from this set, and so therefore in average, so we will have, actually not in average, exactly 1 over p of these subsets will have a remainder of 0 mod p, and 1 over p of these subsets will have a remainder of 1, and so on. So what I'm trying to say that is that the p choose k elements, the p choose k subsets are evenly distributed among those that have a remainder when you sum them in mod p, that have a remainder of 0, that have a remainder of 1, and so on. So therefore, and you can basically do the same thing for the other set y as well. So therefore what we have is the following. So for all r between 0 and p minus 1, there exists a zr, let's call it, right, zr, such that m of zr is congruent to r in mod p. We can always find one of these sets will give me the r that I want, right? So therefore, as I said earlier, as I mentioned earlier, from the p choose k k element subsets, we know that 1 over p times p choose k of these subsets, I should say, have a sum, have their sum of elements congruent to r in mod p. And that same fact holds also for the other set y, when we choose p minus k element subsets. We know that 1 over p choose p minus k of them, of these, will have the sum of their elements congruent to p minus r mod p. But then we can combine these two. R plus p minus r will give me 0, right? So that's the goal. So therefore, overall, how many of the subsets have the sum of their elements altogether equal to 0? So p element subsets is the following. 1 over p of them, p choose k, will have a certain remainder. So let's do it like this. So you pick an r, you pick the remainder for the first set, right? So the r that we described. Once you have the r, so this many of them, of the subsets, k element subsets chosen from the set x, will have a remainder of r, and then 1 over p times p choose p minus k of them, chosen from, so p minus k element subsets chosen from the set y of y here, of x here, will have, so this is a product, all will have the sum of their elements equal to p minus r. So therefore, so we can sum it from k equals 1 to p minus 1. And obviously this will be equal to 1 over p squared summation k equals 1 to p minus 1 of this thing, p choose k times p choose p minus this. But then finally this thing is Right. Now, this was for a particular R, but now we can vary the R, vary R. So R can vary between, it can take P different values, starting from 0 all the way to P minus 1. So as a result, the total number of subsets whose sum of elements are number of p element subsets, I should say, p elements subsets whose sum of elements are equal to 0, congruent to 0, is equal to, I reintroduce the set x and y, so there's a 2 plus, so there are p different values, so I'm multiplying this expression by p, so I will get p times 1 over p squared, then this whole sum, p choose k, p choose k, p minus k equals from 1 to p minus 1, and that's simply equal to 2 plus p times this expression here. Early on we calculated it to be 2p choose p minus 2, so let's plug it back in. 2p choose p minus 2, and that's the desired result. So we have found the number of subsets whose sum of elements is divisible by p, and that solves our problem. Hope to see you in our next video.